Good morning. Let me start by saying thank you very much to Alan Howard and to the Howard Foundation for making this event possible, and also to the organizing committee who invited me to give a talk today, and to James for his kind introduction. I think you got it wrong about the key lime pie. I think you're thinking of Wolfgang Schulk. He's addicted to the stuff. So today I'm going to be talking then about the distribution of light on the retina and its possible implications for age-related macular degeneration. And yesterday, John Paul Sangiovanni was kind enough to quote twice from my work, so I'm returning the compliment today. Together with other researchers from the National Eye Institute, he made the statement that long-term exposure to intense illumination may be among the most relevant damaging factors involved in AMD pathogenesis. So we have this premise then that light may be a risk factor for age-related macular degeneration. And then, of course, we've heard a lot about how macular pigment can mitigate against the damaging effects of too much light in the macular region. Unfortunately, the epidemiology is somewhat equivocal. There haven't been all that many studies, but I've listed a few of them here. I'm sure we're familiar with many of them. The Chesapeake Bay study involving fishermen found a relationship between advanced AMD and either just visible light generally or blue light specifically in the 20-year period prior to diagnosis of the condition. And I'm sure Barbara is even more familiar than I am with the Beaver Dam study, which showed a relationship between early age-related maculopathy, increased retinal pigment, and summer sun exposure. There was a Japanese study looking at late ARM, and they tried to estimate a lifetime exposure to sunlight. And then a little study I came across, this Croatian RAB study, which was conducted on the island of Rab. I'm not sure quite where it is, but they looked at the incidence of age-related macular degeneration and chronic exposure to sunlight by comparing a group of urban dwellers who were presumably less exposed to light on the one hand, and fishermen and farmers on the other, who presumably were exposed to more light. So those are some which I've come across in support of the association, but then we've got some other ones which do not support the supposition. The Finnish study looked at age-related maculopathy and working outside. The Polar study also found no relationship. On the other hand, they did report that the use of sunglasses reduced the risk of soft drusen. And the Australian case control study found no association between AMD and median annual sun exposure. Why should we get this for and against? Well, most people accept that it's extremely difficult to estimate, for example, say, lifetime exposure to sunlight. And then the question becomes, even if you're exposed, even if your body is exposed to a lot of sunlight, what about your retina? Do you squint? Do you wear sunglasses? Are you wearing a hat with a large brim? So it is difficult to determine, say, the cumulative light exposure of the retina, which may, of course, then be important in the development of the disease. Now, we do have a model, of course, for how light could lead to the disease. In this cartoon, blue light in particular excites a sensitizer such as A2E, which is found in the retina, which promotes it to an excited state. It decays rapidly to a triplet state here that can react with oxygen to form the destructive form, which we call singlet oxygen, and that can attack, for example, polyunsaturated fatty acids which are very prevalent in the outer segments. Where does macular pigment come in? Well, of course, macular pigment is very effective at filtering out blue light and hopefully preventing the excitation of these sensitizers. But not only that, the carotenoids generally can deactivate the triplet state of the sensitizer and dissipate the energy harmlessly as thermal energy. And the third possibility is that if the singlet oxygen is in fact formed, then the carotenoids such as lutein or zeaxanthin is effective at deactivating the singlet oxygen, returning it to the ordinary unreactive state, and again dissipating the energy harmlessly as thermal energy. And Janet Sparrow has estimated that 99.95% of the quenching is of this physical type, and only 0.05% is chemical, and that 0.05 chemical quenching would result in, say, the formation of carotenoid oxidation products. And we do know that they exist in the retina, but they're not very prevalent. Okay, so my question is going to be, does the macula, where the disease occurs, receive more light than the rest of the retina? And a lot of us perhaps have in the back of our minds a picture something like this. And with this picture in mind, they say, yes, well, of course the macula receives more light. Look, the rays of light coming in concentrate to a point on the center of the retina, right at the fovea. What's wrong with this picture? Well, this is the sort of ray diagram that we would draw in an optics book for a patient, or rather a subject, say looking at a distant star, where the incoming light is more or less parallel. It's a point-like object and is producing a point-like image right here on the fovea. Whereas, of course, we've got light coming in from everywhere. So when you look at a picture like this, so you've got your wide visual field, it's flooding the retina with light, and you might now look at this picture and say, oh, well, maybe there's a uniform distribution of light on the retina. That's not entirely true, because if you look at a picture like this and look at the diameter of the pencil of rays here that's coming from straight ahead and compare it, and of course it's limited by the size of the pupil, and compare that with the diameter of the pencil of rays coming in obliquely, of course those rays pass through a pupil of which has an effective area less than for light coming straight in. So we would expect then the intensity of light up here to be less than the intensity here for that reason. And a number of people have tried to model the eye and to determine what would be the distribution of light on the retina for what's called Ganzfeld illumination, and this is basically the type of illumination that your eye would be subjected to if you spent your days standing in front of a nice uniform white wall. So your entire visual field was uniform. And mainly because of this effect that I showed in the previous slide, the intensity of light drops off, but it's remarkably uniform, at least out to about maybe 50 degrees. And depending on how sophisticated your model of the eye is, you get either a uniform light distribution out to very large angles, or with the more sophisticated model, it does at least start to drop off. What I did was to take this blue curve, or at least the appropriate portion of it up here, and I've superimposed it on a picture of the retina. Actually, I've folded the curve over. And so what we see here is that over the region of interest, certainly here where we see macular degeneration or maculopathy, there is essentially a uniform distribution of light. And that led Flipson to make the statement in an article in '88 that patterns of illuminance, therefore, and he means retinal illuminance, therefore cannot alone explain the particular preference for macular degeneration with age. But the point is that we do not spend our lives, hopefully, standing in front of blank white walls. And my thought is that it's quite possible that brief periods spent looking at very bright sources of light could have a dominating effect on the cumulative distribution of light on the retina. So I did a sort of back-of-envelope calculation and used as a reference a piece of white paper sitting on the floor of my office, illuminated with ordinary fluorescent lighting, and compared the luminance of that with, for example, the solar disk. And if you accidentally glanced at the sun for only 1/10 of a second, the amount of energy being deposited on the fovea, or in the center of the macula, would be the same as you would get by looking at this sheet of white paper for nearly 3 days. Yesterday, John Barber mentioned a student who decided to look at the sun for, what was it, 3 or 4 minutes. If you do the same sort of calculation, the amount of light that was deposited in that student's macula during those 3 or 4 minutes would be the same as looking at this sheet of white paper for about 20 years. Down here, much less bright, but still bright, is the glare on a car. Looking at that for 1 second would deposit the same energy on the macula as looking at our piece of paper for 1 hour. Looking at the reflection off a concrete driveway for 3 seconds is equivalent to looking at the paper for 5 minutes. So this makes the point then that what you look at and for how long you look at it is going to be critical as far as determining the distribution of light on the retina. So how do we do it? Well, I'm using an eye tracker, commercially available eye tracker. It's worn by the subject. There are 2 cameras. There's a scene camera, which is like a video camera, a little miniature video camera, which captures the scene in front of the subject. And we're going to be using that as an imaging photometer. In other words, using the pixel values that we capture as an indicator of the intensity of the light. The so-called eye camera is actually an infrared sensitive camera. There's a little infrared light source here, so it doesn't upset the subject. And the eye camera captures an image like this, and it actually does 2 things. It looks for it manages to locate the darkest part of the image, which is the pupil. Acts as a very nice sort of black body. And it also measures the diameter of the pupil, because of course when you look at something bright, your pupil stops down and that reduces the light intensity on the retina. So in the subsequent computer code that we write, we incorporate the size of the pupil and follow it as it expands and contracts. Now this, if it'll start, let's see. No, this is supposed to be a movie. Which one would you suggest? Yesterday it started automatically.
Let me go back.
It's the next one. Maybe.
We are getting now.
Oh, pity.
He's coming to help you here.
Okay.
If you want to play this.
There we go. That's good enough.
Yeah.
Yeah. Okay. So, so this is an example of the information that we gather. The scene being captured by the scene camera, and the green dot, of course, representing the subject's gaze position. Looks like it's speeded up a little bit, but sorry about the quality. I think yeah. Well, okay. So that's that.
Okay.
Yep. Thanks. We can go back. Okay. Perfect. Thanks. So before I go on to any results, let me just point out that assuming that a video camera can be used as a photometer, there's a little bit of wishful thinking. This is just a picture taken with that camera, a still picture. What you see in blue is a number which is proportional to the pixel values. What you see in red is the actual intensity at the corresponding position in the scene as determined with an accurate photometer, everything being normalized over here to this dark part of the image. So we've got 1, 1. But if you look up here in the sky, for example, the camera is telling us that cloud or part of the sky is only 5.5 times brighter, but whereas in reality it's 84 times brighter. So at the moment, at best, we can just think of the results that I'm giving you as being qualitative rather than quantitative. The problem is with digital cameras is that they have a built-in so-called gamma. Any of you who are photographers will know what I'm talking about. But it basically is a technique used to compress the range of intensities at the upper level of intensity. If you don't do that, the picture looks really strange. The other problem with a digital camera is the automatic aperture. So if you point the camera at some scene which is not too bright, or you point it at a scene which is really bright, the camera automatically adjusts itself so that the brightest part in either scene produces the same maximum pixel value. So bear that in mind as we move along. So how do we get the information that we want? Well, let's imagine that the subject is gazing at the pink part, that's their fixation point. And the region surrounding it that I've outlined in the rectangle will then be imaged onto the subject's retina with the gaze position, of course, at the fovea. Now, as the person continues to look around at the scene, the gaze position moves, and the part of the scene which is imaged around the fovea is also going to change. Some of the information has to be rejected. You'll notice that sometimes the rectangle moves beyond the region of the scene, and if we included that information, of course, we would get a false reading because it would be taking in information from outside the scene that's being captured by the scene camera. So just to go over this one more time, let's imagine that we have here a particular gaze position. Then that would be the corresponding distribution of light on the retina around the fovea, at least due to that rectangle of light. we have all the scene camera is capturing frames at a rate of 30 frames per second. So let's imagine that this is a sequence of 4 such frames with the gaze positions indicated by the pink dots. So the first thing we do in our computer code is to align or stack the frames one above the other, if you like, with the gaze positions superimposed, and then just simply add up corresponding pixel values. So if you want to know what's the cumulative light distribution right at the fovea, you would take the pixel value here from this image, add it to the pixel value here, add it to the pixel value here, add it to the pixel value there. If you want to know what's the cumulative light on a part of the retina corresponding to this part of the scene, then add this pixel value to this one, to this one, to this one, and so on. We wanted to check to make sure that our system was working, so the first test that we did was to have a subject who was in the know sit in front of a projection screen, and we projected a sequence of photographic images, and we told the subject, each time a new picture comes up on the screen, try to immediately look at the brightest object within the scene. So they did that for a period of about 5 to 10 minutes, and then we calculated the cumulative light distribution on the retina in this 3-dimensional plot. We're looking at vertical field angle here, horizontal field angle here, and on the vertical it's the light intensity, with the fovea being at 0, 0, so we see indeed that the light intensity did peak right at the fovea as we hoped. And then we did the same thing, asking the subject now do the same thing, but instead of seeking out the brightest point on the image, look for the darkest. And lo and behold, we got this picture here with the dip here located right at the fovea. So things seem to be working okay. So the next thing we did was to take a naive subject, so they don't know, all they know is that they're going to be wearing this eye tracker, and they don't know what they're supposed to be looking at. So this was another test. So we presented a video on the projection screen and just sat the subject down and let them look at anything they wanted to look at. And as you can see, for this particular subject, this is a light scale here to give you some idea of the relative light intensity. And again, we can see from this patch here that apparently the subject was unconsciously seeking out the brighter parts of the scene as it was presented to them on the video. What I did with this image was to then try to do a radial plot, an average radial plot of light intensity. And it does show, in fact, that the actual variation in light intensity across the retina was very small. But I took this image and then reflected it and placed it over a picture of a diseased retina. And so we can see then that in the very center, compared, say, with the disk, there was just a small 11% increase in light intensity at the fovea. So another experiment which we did, which produced very consistent results, was to take a group of, again, naive subjects and sit them down in front of a computer monitor. And we said, just do what you want. You can read your email, surf the web, do whatever you normally do in front of a computer, wearing the eye tracker. And with absolute consistency, we got pictures like this, showing a remarkable increase in light intensity at the very center. So again, I produced an average radial light intensity plot, and that showed a more pronounced peak at the fovea at 0 degrees. And again, I've taken that curve and reflected it to the left and superimposed it on a diseased retina. And in this case, we now see that there is a 110% increase of light intensity at the center of the fovea compared with out here, just beyond the disc. And it's interesting to look at this picture and compare it with the area of damage produced by macular degeneration. So now, not only do you have to worry about using a cell phone and giving yourself brain cancer, but you have to worry perhaps about using your computer and getting age-related macular degeneration. No, just kidding. But we might sort of look at this and say, well, what about the time that we spend doing a similar activity, looking at a TV, similar sort of light levels, and presumably producing the same sort of uneven light distribution on the retina. It's just the same curve superimposed. I'm not sure. Somebody can correct me whether this really is dry AMD or not. The real test then was to take subjects, and again naive subjects, and just let them wear the device and send them walking around the campus. The device actually has wireless connectivity, so we can. It's not too difficult to use. We can just send them off, keep them within line of sight, and we can actually collect the data. So this was one of our subjects who was sent on a walk, and when he came back, we analysed the data, and this was a subject who indeed did seem to spend more time looking at bright objects rather than dark objects. This was the average radial distribution. They look better on the coloured pictures, don't they? And this was the picture superimposed, or the curve superimposed on the retina, showing a 22% increase in light. And you have to ask yourself the question: well, it may be a small increase, but maybe it's significant as far as the development of macular degeneration is concerned, if light is indeed a contributing factor. But I've given you probably the best looking data, because it didn't always work out that way. This is another subject that we sent off for a walk, and although, well, for some reason there was the brightest region occurred up here in the inferior temporal part of the retina. Again, a radial plot, and on average a 7% increase in light intensity at the center. So that's where we stand at the moment. And with all of these results, bear in mind that earlier slide that I showed you, which demonstrated that the video camera is not really a recording photometer. And so where we see here a 7% increase, perhaps when we get things really sorted out, that might turn into a 70% increase. I took the data which produced the biggest peak. That was the subject who was sitting in front of a computer monitor. I thought it would be interesting to calculate what would have to be the macular pigment optical density distribution, which would essentially flatten that light distribution on the retina. And it looks like this black curve here. So it's actually, you would need a very, very broad macular pigment distribution if the purpose of macular pigment was to sort of flatten out the light distribution on the retina. Down below in color, you see some actual macular pigment optical density distributions obtained by reflectometry. So they're generally much narrower. But again, remember that this upper curve may in fact be much more peaked because of this problem with using the camera as a photometer. So, in conclusion then, I think I would have to say that increased light on the macula, we can't say that it's a general phenomenon that occurs for all people under all situations. However, increased light on the macula might occur always during specific tasks, such as sitting in front of a computer monitor or watching television, maybe even too much use of the cell phone, or having a profession. Perhaps an arc welder might have an increased light intensity in the center of the macula. But it did seem that from the experiments we did where we just sent people off walking around the campus, that for some individuals they did seem to seek out particularly bright areas and spend more time looking at them. And now finally that the macular pigment can compensate for increased light, not generally, but certainly it does, of course, in the cone-dense center of the macula. And I'm finishing up with this question that maybe the propensity for macular degeneration is the result of a higher concentration maybe of either photosensitizers or vulnerable tissue, or both, in the macular region. So I'll leave you with that thought and just acknowledge my student collaborators, Jorge Gibbert, many of you have met at the Macular Dinner, and Anaban Mukherjee. Thank you.